All right, let's jump right in. For decades, our entire digital world has been built on one thing, silicon. But that incredible era of computers getting faster and faster every year, well, it's hitting a wall, a hard one. Today, we're going to explore a revolutionary technology, one that operates near absolute zero to deliver speeds and efficiencies that silicon can only dream of.
You've probably felt this yourself, right? Remember when each new computer felt like a massive leap into the future? That feeling is kind of faded, hasn't it? And it's not just your imagination. There's a very real, physical reason why we've hit this performance plateau.
So here's the core of the issue. Moore's law, the idea of cramming more and more transistors onto a chip, is kinda still alive. The transistor count keeps skyrocketing, but look at the clock speed, the actual pace at which the chip thinks. That flatlined way back in the mid-2000s. So what gives? It's the wires. The tiny little interconnects that link all those transistors are creating a massive data traffic jam. The smaller you make them, the more resistance they have, which generates heat and throttles their speed. It's like we've built a bigger, denser city, but the speed limit on every single road is stuck at 10 miles an hour.
To break through this wall, we need a completely different kind of road, a superhighway, really. And that's exactly where superconductor electronics come into the picture. This isn't just a tiny improvement, it's a fundamental shift in how we build computers, and it promises to solve both the speed and the power crisis in one go.
And the properties of this tech are, well, they're almost magical. We're talking clock speeds in the tens of gigahertz, way beyond what silicon can do without basically melting. The amount of energy used for a single calculation is fantastically, absurdly low. And best of all, those data traffic jams we were talking about, poof, gone. With near-zero resistance, information just flows like a bullet train.
The heart of this entire technology, the magic ingredient, is a device called the Josephson junction. You can think of it as the transistor of the superconducting world. It's an incredibly simple but powerful quantum device. Just two superconductors with a tiny, wafer-thin insulating gap between them. This little switch is what makes everything else possible.
So how does it actually work? The best analogy I've heard is a pendulum. Normally, it just hangs there, in a stable state. But you give it a tiny push, a small bit of input current, and whoosh, it swings all the way over the top. As it does that, it releases a perfectly formed tiny pulse of energy. This pulse is called a single flux quantum. And that pulse is the digital 1 in this new computing language. It's an unbelievably fast and efficient way to process information.
Now, this all sounds amazing, right? So the obvious question is, if this stuff is so great, why isn't it in your laptop right now? Well, for decades, this incredible promise has been stuck in the lab, held back by a few massive and what seemed like insurmountable challenges.
Challenge number 1, density. I mean, just look at this. Using the old-school superconductor logic, a simple 4-bit logic unit, something utterly trivial by today's standards, took up a massive 25 square millimeters of space. That is gigantic. You could never build a complex modern processor at that scale. Just no way.
The second problem was power. And this is kind of ironic because the chips themselves are incredibly efficient. The issue is the bias current, this constant stream of power you needed just to keep all the switches on and ready to fire. To get just 10 million junctions ready to go, you had to pump a staggering 350 amps of current from room temperature down into the cryogenic system. That's an insane amount of power, an absolute engineering nightmare.
So, you can really boil it all down to these 3 big hurdles that kept this tech on the shelf. The circuits were huge, they needed a fire hose of power just to stay on, and there was no practical, high-density memory to go with them. Without solving these, superconductor computing was just a fascinating academic exercise.
But what if you could fundamentally change the building blocks? What if you could redesign the Josephson junction itself to solve these problems from the ground up? Well, that's exactly what researchers did, and it led to a series of breakthroughs that are finally unlocking this technology's incredible potential.
Meet the hero of our story, the pi junction. That's pi like the number. It's a special type of Josephson junction with a tiny magnetic layer embedded right in the insulator. Now, this might seem like a small change, but it has a profound quantum effect. It creates what's called a pi phase shift. All that really means is it has a built-in energy state, which allows it to function without needing all the bulky external inductors and resistors that made the old circuits so enormous. It's a game changer.
This new pi junction is the key that unlocks an entirely new way of designing circuits, a whole new logic family called fast phase logic, or FPL for short. It's a complete rethinking of how you build superconducting processors.
And the results is just stunning. An old logic cell was about 30 by 30 micrometers. The new FPDIL cell, built with these P-junctions, is just 1.8 by 1.8 micrometers. That's a reduction in area of over 270 times. Suddenly, that density problem is no longer an insurmountable wall.
To put that in perspective, this chart compares these technologies to a standard 12-nanometer silicon process. The old RSFQ technology was a staggering 10,000 times larger. It was even in the same league. But FPL, it's still larger than silicon, sure, but it's only about 30 times larger. It's in the same ballpark, a massive leap that makes complex chips actually feasible for the first time.
So, with these new, compact, and super efficient building blocks, what can you actually build? Researchers put this new FPL technology to the test by designing a critical component used in everything from 5G communications to medical imaging. The case study was a fast Fourier transform, or FFT, processor. This is a real-world, computationally intensive task. Designing one of these is the perfect way to demonstrate whether this new logic can deliver on its promises of speed and density in a practical application. And the results, well, they speak for themselves. The old RSFQ tech could get to a 15x speedup over silicon, but at a ridiculously large area of 1,000 square millimeters. The new FPL technology, it achieves a massive 40x speedup over silicon in an area of just 15 square millimeters. It's dramatically faster and dramatically smaller. This is the proof.
But what about that third hurdle, memory? The solution there is another innovation called bistable vortex memory, or BVM. It's a completely new memory type that's compact and can be arranged in a grid just like conventional RAM. And best of all, it's non-volatile, meaning it holds its data even without power. This was the final missing piece of the puzzle.
So, with these core challenges of density, power, and memory now solved, the path is finally clear. Superconductor electronics are moving from being a laboratory curiosity to a viable technology for the next generation of high-performance computing.
The roadmap from here is all about engineering and scaling. First, developing a complete library of standard logic cells, like Lego bricks for designers. Next, integrating these logic, memory, and control systems together across multiple chips. And finally, scaling it all up to tackle the last few architectural hurdles before it can be used in the supercomputers of the future.
And that brings us to the final, crucial question. This isn't just about faster computers for the sake of speed. This is about efficiency. A system that is hundreds of times more power efficient opens up entirely new frontiers. So, think about this. What could we achieve in climate modeling, drug discovery, or artificial intelligence if the enormous energy cost of computation was no longer the limiting factor? That's the future this technology could make possible.